7.1c, Newton's Law of Universal Gravitation, worksheet, do number 1A only. You can do B if you want, number 3 and number 4. If you really want to do number 2, you can, but it's not really necessary. Okay, this is absolutely amazing, this lesson, the material, and I wish I could tell you more information about it, like more history and the incredible realization of Newton. I will talk about more about him in future lessons. It kind of opens up this a little bit. But well, I'll read the note for where it starts off here. It says, about 45 years after Kepler published his laws, 45 years later, 1666, Isaac Newton began to study planetary motion. He found out that in comparing the sun with the planet, well, he found the mathematical relationship between gravity and the size of the mass of an object. And that's pretty amazing, thinking about he could not find the mass of Jupiter or the mass of Saturn or anything like that. But he was able to calculate the mass of the moon. He was able to estimate what it was, and he was right about on it. And that's amazing in itself. But he wasn't able to get the mass of the Earth. If he had been able to find the mass of the Earth, then we would have been, if Newton had been able to find that one thing out, the mass of the Earth, I'm just telling you now, in his day, we would probably be about 150 years, it would have put scientists 150 years ahead. So it took 150 years before we could calculate the mass of the moon. With an experiment that a scientist named Cavendish did after Newton. If you're just like really wondering, you want to read about that, it's in 7.2. There's a picture of him. And I'll talk about him either in class or in a lesson. I'll talk about what Cavendish did to kind of break the code of Newton's law. I'll show it to you in a minute, and I'll tell you what he did, but I'm not going to go through Cavendish's experiment yet. Okay, so, everyone's always heard the story of saying, well, Newton was sitting there under a tree, and he saw an apple fall. And maybe it was an apple or something that fell, or maybe it was the way it fell. Maybe it was a wind blowing or whatever it was. But it made him think about the same thing about the moon. I guess he thought about planets. He thought, hey, what if the moon is falling to the Earth, just like an apple would fall to the Earth? What if that's happening? And you might say, well, wait a minute, is the moon falling? Actually, the moon is falling to the Earth. However, don't get scared. Its fall matches and creates the curvature of its orbit. So we'll talk about that later on, and I'll explain it, and we'll talk about circular motion that we talked about at the very beginning of this unit. How like swinging a little ball around a string. It's just kind of what's happening to the moon around the Earth, and for that matter, what he said is true for any moon around any planet, or for planets around the sun as well. So anyway, here his, I'll just show you, yeah, it was believed he saw that falling apple and that made him think about it. Now, it also tells you in here, you may not know this, that all of this physics book, pretty much everything we will do in general physics, most all of physics, I'll say that, it was all put together and we can all thank Newton for it. He wrote this thing called, I can't remember, he wrote the name in Latin, but it was like Encyclopedia of Science Knowledge, all these volumes. And what he did was, he went way back as far as he could find ancient history and found everything about math and science that had ever been done. Principles of math and science, Principia or something like that. Anyway, you can look on the internet and find out about it. But he wrote this. So what Newton did was he said, like, okay, I'm going to take every scientist, everything I can find about math and science, I'm going to put it all together in these volumes. And that's what he did. And in doing that, he understood and learned everything about it. And so he expanded on it incredibly. And it was a revolution. I mean, you've always heard about Einstein thinking, wow, he's like the smartest guy and all this. And what he did was incredible. And it's true. But I think Einstein also would tell you Newton. I think Newton is like, I'd heard before that he always had a picture of Newton with him or something like that. I heard it just recently in his office or whatever. Newton was like the one. It's like, Newton, you might say, is even more influential, even than Einstein, because even though Einstein proved some of Newton's stuff wrong later on, but Newton is more influential because everything we have today, technology, everything, you pretty much can base it on Newton. Pretty amazing. Okay, what he did. Technology, airplanes flying in the air, machines running and all that. Newton. Okay, so I didn't tell you, most of your calculus, most of your physics book was by Newton, written by Newton, or compiled, but he made it easier to get, understand. How about this? If you were to take calculus, calculus was invented by Newton to make the physics a little bit easier in the math. You might think, what? It actually is that way, but I don't teach calculus physics. Also, a lot of trigonometry and pre-calculus you can thank Newton for. So Newton, physics that you get to take in high school, calculus you take in high school, pre-cal you take in high school, Newton, you can thank Newton or blame him. Don't get mad at your teachers. Think about Newton. Okay, here is the law. Okay, and you'll like this. It's fun. It's kind of a neat thing, and it's fun to think about it. We'll spend more than one lesson on it, and then we'll talk about even how to kind of break it down and understand it. There it is. So the force of attraction. Well, first of all, here's a neat thing that you would not think of, but here's what it says. Any two objects. Now I have these little molecule sets for my chemistry, but any two objects that you can think of. It could be this little ball, molecule ball, this little atom, and atom, or it could be this atom, and here's some bottle of chemicals that I have. This bottle and this atom. Any two things attract each other. You might say, wait a minute. If I sit next to each other, you mean they're going to move closer together? Well, as time goes by, they would. Now, if the friction is too great, it wouldn't happen. So Cavendish found a way to prove that by taking two lead ball, imagine two small, somewhere between a bowling ball and maybe like a pool table ball, really heavy, maybe a shot put, with the thing that they throw in the Olympics is really heavy. But he took two of those suspended, and I'm kind of telling you about his experiment, and he did measure, and they do attract. Pretty amazing. So two objects will attract. They don't have to even be charged. Now, if there's positive, negative attraction, that's different. But gravitational attraction, any two masses really do attract. Now, the amount of attraction that you have is very, very small, and the force is very small, unless, and you can't notice it, unless one of the objects is really gigantic. So how about if I'm taking this little, well, I'll take this one, the red. If this little atom is one object, and the Earth, well, it's the ground below me, is another one, look, wow, they attract, and you can notice it. Oh, you didn't think about that. But when you drop something, it's attracting to the Earth. Now, you don't ever think about it that when you drop an object, even that the Earth is attracting to it. But that's also true. So the Earth, when I drop this, if you jump off, just say if you jump down a few stairs, you just, you're going down the stairs, you jump 3 or 4 steps down, okay? Are you falling to the Earth, or is the Earth is falling up to your feet? It's really, you could say it's a little bit of both. But now, the thing is, since all around the world people are walking or jumping or airplanes are landing and all that, or objects are falling down and all that, it all cancels out around the Earth. You can't really say there's anything significant that would happen. But if there was nobody at all on Earth, okay, no one on the entire Earth, and then an airplane flew above and somebody jumped out parachuting down, that person coming down, perhaps, I don't know, depending on how fast they're going or whatever, but then they slow down though. But could you measure the amount that the Earth would move up? It would be very small, its motion change compared to the person falling, because the mass is so large. Okay, so here it is. The force of attraction, gravity, you can say the gravitational force of attraction depends on, forget about that for a minute, the mass of object, I like to call it mass of object A, mass of object B. All right, so you have object A and object B, one with B larger. And then R is the radius, the distance between them. Now, when we say the radius, we're not talking about the radius of A, halfway to A or halfway to there. We're talking about the distance from center to center, the orbital radius. So if it is an ellipse, it doesn't really matter. What really matters, we can imagine it being a circle, because we're going to always put, the radius we're going to put in there will always be the average all around it, the average distance it is. Okay, you always, the word mean. So when you see the mean distance, mean means average. That means the average radius, as it goes around the sun or whatever, or the moon around the earth, whatever. Okay, so that's how far they are apart. Now, here's an interesting thing that notice the bigger the radius gets, if this number gets really, really large, what's going to happen to your overall force? If that number gets really large, this number divided by a larger, larger, larger number, well, it's going to get smaller. Your force gets smaller and smaller. And that makes sense because you know that on the Earth, your weight is one thing if you're standing here on Earth. My little friend here will draw. But if we put her like thousands of miles away on the space station, whatever, now we weigh her and she weighs a lot less. And farther, less. So her weight relative to Earth gets smaller. So as the radius gets larger, if this number goes up, your overall force goes down. We'll talk about that in another one. The other thing that makes sense is the mass of the two objects matters as well. So let's put her back in space again. Well, no, it doesn't matter. She can be in space or on Earth. What would she weigh on Earth, but what would she weigh on Jupiter? Think about that, okay? I'm making her bigger. She's not going to be any bigger. But I was drawing it quick. So yeah, your weight on Jupiter is about double what it is, more than double, a little bit more than double what your weight is on Earth. What does that mean? The vicinity. I know a lot of it's gas here, but there must be some solid in here. There is, because the gases wouldn't be enough. Or could they be that dense? Yeah, there has to be a strong gravity pulling those gases as well. So yeah, there's a surface somewhere there. So anyway, but the Jupiter would be much greater because the mass of Jupiter would be really, really big compared to her, and the Earth would be big as well. Okay, now what is this thing G? So here's what's amazing, and you know that Newton, all of his life, he had to want to figure this out. This had to be something he was thinking probably all the way till the day that he passed away. He was like thinking about, how can I figure out what that is? This is called the universal gravitational constant. It's kind of like pi equals what area is 2 pi. The 2 pi r is the circumference. Area is pi r squared. Pi 3.14 is a constant. You know that. If you took the gas chemistry, like the gas laws, or something called PV-nRT, R is called the gas constant. There's a number, a universal number to plug in. Well, there's one here as well that makes this all true. You can calculate the force in newtons, or you can change it to pounds if you want to. And as long as you know the mass of the mass of the two objects that are being attracted and how far they are apart in meters. Mass in kilogram, distance in meters. Then you got to put this constant number in and it works. So Newton was not able to figure that out, okay? And it took a man named Henry Cavendish, amazing as well, that came up with an experiment that worked to measure it, and he plugged it into all of Newton's stuff. And like I said, the day he did that, probably the next day or whatever, as soon as people got Cavendish's answer for that number, they could immediately plug it into the equations and they could find out, we know the weight of the Earth. We know the weight of whatever. We could probably planets, all this stuff, immediately they knew. Okay, and we'll talk about that later on. Okay, so let's do a little bit of problems with this calculation. They call it an inverse square relationship because the weight is proportional to the inverse. That means 1 over the square of the distance between them. Okay, so that's what that was a neat thing that he figured out. So Newton figured all this part out, but he just couldn't get that, I guess, is what it was. From my knowledge, we couldn't. Okay, A. So what is the gravitational force that the moon exerts on a 70 kilogram astronaut visiting the moon? And it says the radius of the moon is 1738 kilometers. I want to show you one other thing before I start, because this is in your notes. Sometimes distance can be in AU. That means Astronomical Unit. I have to say, I went to school. Auburn University is the name of the school where I went. Do I have my little Auburn thing up here somewhere? I don't have it to show you. I have a hat. I can at least show you that. But anyway, well, it has nothing to do with it except the letters AU. AU, Auburn. There it is. Okay. Anyway, most of the time they wear blue. Sometimes they wear all orange, but orange and blue is the colors. Okay, so AU. But an astronomical unit, this is on your worksheet as well. Let me write the number down because I don't have it memorized. It's 1.50 times 10 to the 8 kilometers. 1.50 times 10 to the 8 kilometers. 1 AU equals 1.50 10 to the 8 kilometers. Now what this is, they just wanted to pick another unit to use for the solar system and for all of space when we study space. And so instead of putting a meter, because meters are so small compared to how far Earth from the sun or Earth from the moon, so they call this the distance between. This is the distance between the Earth and the sun. It's called an astronomical unit. So if, for example, and you're going to see it on your worksheet, it's not on this problem, but I wanted to show you. If we said you had 2.5 AUs, what would that be in meters? Let's go to meter, because usually you have to put things in meters. 2.5 AUs. Well, from AU, I can go to kilometer with this. 1 AU is 1.50 10 to the 8. I should give it to you in meters. If it's that many kilometers, it'd be 10 to the 11th for meters. I don't know why I didn't do that, but oh well. I did this on your worksheet. I think I probably got it from another textbook. And, I would say it's good to know 10 to the 11th. You're probably not even going to see in meters, but oh well, we'll go with that one. Because 1 kilometer is 1,000 meters. So, if we say something is 2.5 AUs away, times 1.50, 10 to the 8, times 1,000. It's a really big number, but 3.75, 10 to the 11th meters. That's how 2.5 astronomical units would be. Double checking it. 3.75, 10 to the 11th meters. Now, the reason why I tell you is because there's a problem on your homework. It'll say how far the Earth or Jupiter or whatever is away. If they said something was 7 astronomical units, well, you have to put it into meters to use that equation up here. And you can just use 10 to the 11th meter if you want to. But I'm not really planning on doing that a whole lot to you. I mean, this came from a book. And so just know that one day, you might take physics or astronomy or basic intro to astronomy, and you might see that come up again just so you'll have been exposed to it. Okay, but anyway, back to A. So what is the gravity between the moon and an astronaut on the moon? So if this is the moon, hey, and I'll draw my astronaut friend that I showed you before, Lily. Okay, I know she's a little bit out of proportion there, but oh well. There she is on the moon. Okay, now, so what is the gravity between her? So I need to know the mass. So how could you find your weight on Earth based on Newton's equation? You can actually do that too. You have to know the mass of the moon, the mass of the person, mass in kilogram, and then you need to know how far they are apart. We'll say center to center, but you can pretty much just use her feet. The radius of the moon would give it to you. And so they say that the radius of the moon is 1738 kilometers. It says equatorial. Okay, so radius equals 1738 km. That's interesting they give it to you that way too, because that would tell you that the moon is not a perfect circle or sphere. It's the best word. The Earth is not either. And the radius, if you go around the Earth on the equator, if you were to walk somehow, even go over the water, whatever, but if you went all on the water around the Earth and then on land as well, around the entire equator, you would go a longer distance than if you went on the Earth and you just went all the way to the North Pole, down, and came all the way back again. Say you go north and south and all that. One circle around the north to south hemisphere would be smaller distance, okay? Because the Earth is shaped that way. I mentioned that earlier. Okay, here we go. All right, so here we go. What is the force on them? And they give the mass of each one. So I'm just going to plug them into here. The gravitational constant is 6.67, 10 to the negative 11. And it says Newton. And then on the bottom we put meters squared, kilograms squared. Now this is something I do in chemistry, AP chemistry, even general. Sometimes I give you this weird constant. Remember a constant. Constant means it's always that number. If you just want to plug that number in, that's fine. but it's a good idea to write Newton, m squared, kg squared on the bottom. This is only a number that makes the rest of the equation true. You don't have to try to understand what it means, okay? And, oh boy, my little Lily friend, I'm going to have to move her over. Oh well, I'm going to run into the math, but you can remember that picture. Okay, now, I even like to put brackets just to be careful. So, and actually, I also like to do this too. It's the moon and an astronaut. So, maybe M moon, or just M for moon, and astro, moon and astronaut. Okay, so the mass of the moon, we'll put that one first, is 7.35 10 to the 22nd. And it's kg. The mass of the astronaut is 70 kilograms. Well, this wouldn't be a little girl then. Lily would be a lot larger now. All right. And let's just see here. It says the radius is 1738 kilometers. I don't know why. Well, again, I think I got it from a book. It has to be in meters. So I don't like to have to mess you up with this, but 1738 kilometer. Change it to meters. So 1 kilometer equals 1,000 meters. So that's going to be 1738, and just put 3 zeros on it, meters. Or if you want to write 1.738 10 to the 7th, right? You can do that too. On your calculator, you got to type it in that way, because that's how you got to put it. I mean, you can type all that in your calculator if you want to, but it's just a lot more work. And then you got to square it. Wow. So yeah, the math is kind of crazy on this. So 1.738 10 to the 7th power meters. Has to be meters down there. Now you can see why I tell students it's a good idea to write the units for G, because watch this. Meter squared, well, that's going to be meter squared when you get it, so that's going to cancel out. Kilogram squared, we have kilogram. Squared on the top, squared on the bottom. So that'll go away with that. Meter squared here will cancel with there. I'll just tell you, anything you see twice will cancel out, okay? Let me just say it that way. But what's going to happen is, wait, hold a minute. Meters must be on the top, and I must have put it in the wrong place. Yeah, it is. I'm sorry. Look at me. Newton meter squared, and then kilogram squared on the bottom. Yeah, that's how it is. So meter squared on the top. I said top and bottom, and that's squared. And you're left with N, because your answer will be in newtons. So I'll keep the N like that. All right, so let me try to do the math. I really hope I do the math right. I'll do it twice. So what I'll do is, first I'm going to square this number. 1.738 10 to the 7th times itself. It's 3.05. No, 3.02. Try it again. 3.02 times 10 to the 14th. Maybe I'll take a little step here. So, because the math is a little crazy here. 3.02 times 10 to the 14th. You know, when you put those times itself. Now, the top numbers, when you multiply them, 7.35, 10 to the 22nd. Oh, and hopefully you didn't forget this, but 7.35 exponential 22nd. That's how your calculator will write it. Times 70. 5.145 10 to the 24th. Okay, now let me just really quick, 1.738 10 to the 14th. No, 1.738 10 to the 7th squared is 3.03 10 to the 14th. Yes, 7.35 10 to the 22nd times 70 is 5.145 10 to the 24th. Yes, I can make it 3 sig fixed because of that. But then, okay, now I'm going to multiply that times that, divide by that, and that will be my answer. A lot of work here. So times 6.67 10 to the negative 11, and then divide by 3.02 10 to the 14th. Uh-oh, okay. Okay, I got, wow, wait a minute. 1.14. I got one, that's got to be wrong. I messed up. 6.67 10 to the negative 11 times 5.145 10 to the positive 24th divided by 3.02 10 to the 14th. Is that really 1.14? Okay. 1.14 newtons. Between the moon. Oh, okay. Yeah, that sounds right. Between the moon. I guess my mind was thinking about Jupiter for a minute, okay, and how big it is. No, you're going to have a very small weight on the moon. You know that. This is the moon and an astronaut. But okay, so 7.35. I don't know. I can check it again, but I'm doing it so many times. You can run past this. You're like, what is going on, Bella? Keep checking your math. Because, see, in class, somebody can do it along with me and can say, oh, Bella, you forgot that. No, it looks like it's right. 1.14 newtons. That means that the girl would not even weigh, not even a pound. It's pretty amazing. Okay. All right, very small. Okay. There it is. Okay, that's your first one, A. Now, the gravity force between two objects, a person standing on the moon. If you put in your mass on the Earth, and you can do that with your own equation with the Earth, the mass of the Earth, the mass of your body, and you can figure out how far the core of the Earth, the center of the Earth is. Now, that's a neat thing, too. How could you do that? Well, if you knew that, you could figure out how far it is if you knew the mass of the Earth. So there's a lot of neat things like a puzzle you can put together. Okay, I'm just thinking about that. Number 2 says, what is the force that the 70-kilogram astronaut exerts on the moon? It would also be 1.14 newtons, believe it or not. So see, 1.14 newtons, not in a pound, pulling the moon, that's very small. Okay, that's almost nothing for how big the moon is. I hope I didn't type some numbers in wrong. I don't think I did. Okay, so I'll just trust I didn't. But if I find a mistake later in class, we'll say, wait a minute, what was that? Okay, so far I've kind of caught myself if I've made mistakes in the videos. All right, B. What is the gravitational force between 6.8 kilogram bowling balls that are 21.8 centimeters apart? You know what? I don't think I need to do that because it's the same thing that we saw. But I'll just set it up because I think you have one like it in your work. But if each of the balls weighs 6.8 kilograms, so it'd be 6.8 times 6.8. And then remember, 21.8 centimeters, you got to turn that into meters. Now see, this is a good example of why do they have all these conversions in metric? Because if you're going to measure two bowling balls, how far they are apart, you're not going to put that in like kilometers or meters. Meters is really, really large. A meter is really far apart, like a yard. So you're going to measure it in centimeters like that, and maybe they're doing an experiment like Cavendish. So it'll be 0.218 meters. You change it to meters. And of course, that'll be squared. And then you put in the 6.67, 10 to the negative 11 constant there. So I always say brackets. This times this, divided by that, times that. We'll give it to. Well, I've already got the problem. Should I just go on and do it? I guess, why not? 0.218 squared, 0.07475. So it looks like a very small number, 6.50, 10 to the negative 8. That's really small. 0.218 squared, 0.0475. I'm just double checking it. I got the same answer again, so I think I did good with that. 6.50, 10 to the negative 8, not meters, newtons. Because all the others, I did real messy this time. You see me leaving off the units and stuff, but I like to put them there. Okay, and then I'll just do one more problem. And this one is a little bit more difficult, but this is an interesting thing. It shows you, it's kind of like once they figured out G, now it's kind of like a puzzle. Like the periodic table was a puzzle for scientists to figure out each element. Well, now if you know what the moon is, sorry for real loud, I can't think I can do that again if I tried. Whistled loud. Once you know the mass of the Earth and then the moon, you start plugging these in, you can find the distance between the mass and the Earth and the moon and all that. So a lot of this was based on like Kepler's data, a lot of what we know in early planetary motion astronomy. So they took puzzle pieces and they were to figure out how much things weighed and how far apart they were from each other. And they still can do it now. It's amazing. All right, so here we go. So it says for number B, part 2. One bowling ball is moved, so the two have a gravitational force of 5 times 10 to the negative 8. So now we know the force between them. 5 times 10 to the negative 8 newtons. And put in your G, 6.67, 10 to the negative 11, Newton, kilogram squared over meter squared. Okay? Times, and it's going to be, each one weighs 6.8 kilograms. So they move them apart, and they want you to find out now what is the distance they moved apart. It's like an algebra thing. You might think, why do you want to do that? Well, I told you a moment ago. Let's just say if you knew, you figured out somehow the gravity between the Earth and the Moon, or whatever it might be, and now you knew the Earth and the Moon's mass, or the mass of two things, okay, M A and B, whatever. And now you can find out how far they are apart. So it's really neat little thing to use for astronomy. Okay, so let me take a little math step here, and I'll multiply all the top there. It doesn't really matter on this one because you have the r squared on the bottom. So 6.67 10 to the negative 11 times 6.8 and times 6.8 again, because there's two masses. MA and MB, whatever. Bowling ball number 1, number 2. If you want to use 1 and 2, that's fine as well. I like to use letters instead of numbers if I'm putting a subscript or something, because I don't want to accidentally use that number in the math. All right, so 3.08 10 to the negative 9 over r squared. That's what it looks like it is. Let me double check it. So this times this times this. 667 10 to the negative 11. Times 6.8 times 6.8. All right, that's going to be 3.08 10 to the negative 9. Okay, now this equals this over r squared. So then you bring the r to there. So now it becomes algebra, which I don't always show you all these steps, but I like to do it every now and then, at least once, or in class when I go over a problem, just for anybody that might have a problem. So you're going to divide by this number that is in front of r, so that you get rid of you isolate r. So 5 times 10 to the negative 8. And then, just want to make sure I copied it right. Yes, 5 times 10 to the negative 8. So then r squared equals 3.08 10 to the negative 9 divided by 5 10 to the negative 8. And I get 16.2. But then don't forget r squared. So you got to get the square root of both sides. And r will be the square root of that. It'll be 4 something, right? 4.0, pretty much 4. 4.02 meters apart. So the bowling balls had to be 4.02 meters apart. And again, with that small gravitational attraction, that many newtons. If you want to put force of grav there, that helps you, that will be good as well. But anyway, there it is. Okay, so you can do now number 1A, 3, and 4. You can actually do 1A and B and 2 if you wanted to, but it's a lot more math work. And what you can do is you can wait till I give you the answer key and just look at them to see if you know how to do it. Well, hopefully it's kind of neat. We'll say a little bit more about this in the next lesson. There's a little bit, believe it or not, there's a little bit of a thought, like non-math kind of thought process worksheet with this too that we probably will do. So that is all. I will see you guys.